Welcome to another circuit assembly tutorial. In this video we'll be building a simple latching intruder alarm circuit. To build the circuit we'll be using a double pole, double throw relay, a piezo buzzer, a few diodes, a PNP style transistor, some resistors, and a momentary button, a normally open momentary button, as well as a 12-volt power supply. The way this circuit will work is you would have it mounted near your door, have some mechanism pushing down on the momentary button. It can be as simple as those who have seen my non-latching intruder alarm video know that I just put a ruler to push this down. Really crude, you'd want to do better than that. But you just have something mounted to the door pushing the momentary button, and then you add power to the circuit. At this point the circuit is armed, but it's in its inactive state. And the way it works is as soon as that momentary button is released, the piezo buzzer will start alerting, and it won't stop even if the momentary button is pressed again. That it latches closed so that power is still being fed to the coil of this relay, and in turn still energizing the piezo even if the momentary button that initially triggered it is pressed again. And the only way to deactivate it once it's alerting is to remove power from the circuit itself. Like one could mount a toggle switch and hide it inside the power or ground line to the circuit itself, and that's the only way you'd be able to reset it after it's in its active state. To demonstrate that, it's a little loud. Note that I could press that momentary button as many times as I wanted to, and it would do nothing to stop the piezo buzzing. The only way I was able to stop it is to actually remove power from the circuit itself. And like I said, one would just need to add a certain toggle switch inside in series with the power line or the ground line. Let's look at the schematic, walk through how it functions, and then build the circuit. The schematic for this circuit is fairly straightforward. We'll have our 12-volt power supply with some form of toggle switch to disconnect and reset the alarm once it's alerting. You'll just have some sort of switch in the circuit. I won't actually be adding this into the circuit as we build it. I'll leave that for viewers to do. That's fairly straightforward. Just put a toggle switch in series with either the power or the ground line, and as long as you cut the high potential off of the circuit or the low potential, it'll deactivate the entire circuit. What we would have, just looking at the schematic, is the unarmed inactive state of the circuit. That's what this diagram demonstrating. We'll have our momentary button, which it serves to arm our circuit, as well as that toggle switch. We have to have both. We'll have some resistors, that PNP style transistor. I'll be using a 2N2907, but you could just as well use a 2N3906 or some other small scale PNP transistor. You'll just need to pay attention to your pinouts. With the emitter of that PNP, it'll be to the positive voltage supply. The collector will be toward the load. We'll also be using some diodes. Now I'm using a 1N5819 Schottky style diodes just to minimize the voltage drop across these diodes when the alarm is activated and alerting. But you could just as well use 1N4001s or 1N4148s. They'll just have a larger voltage drop. Schottky, these I'm using, have a 0.3, 0.4 voltage drop, which, why would that matter? Ultimately, it just will enable the circuit to alert a little longer as the 12-volt supply diminishes. They'll give you a few tenths of a volt longer operating period. And we'll have our double pole, double throw 12-volt relay. I'm just using a fairly standard one from RadioShack. I'll put the part number in the description. It'll have 6 pins on one side, 2 pins for the coil on the other side, double pole, double throw relay. That's all one would need. And then a piezo buzzer. And I have the part number here, but I'll also put it in the description. Let's walk through each of the states that this circuit can be in and see how the current, in terms of conventional current at least, would be flowing during those states. This is the unarmed inactive state. The momentary button is released, but there is no power applied to the circuit. The next state this circuit could be in is what I would refer to as the armed inactive. We just saw the unarmed inactive. This is the armed inactive version of the circuit, where the switch in the power line is pressed down. So we have power to the circuit, as well as that normally open momentary button has been pressed. It is closed. What's happening in the circuit at that point? Not a whole lot, besides the base of this PNP transistor is being pulled high. We'll have voltage coming from the 12 volt supply across the contacts of the normally open momentary button through the 1K to the base of that PNP. And remember that a PNP transistor will not conduct across its emitter and collector unless its base is 0.6, 0.7 volts lower than whatever voltage is sitting at its emitter. And in this case we have 12 volts at the emitter, we'll have 12 volts, very close to 12 volts at the base, and that'll be enough to pull the base high, keeping this PNP from conducting. And if it's not conducting, nothing's happening with the relay. Here's the active state, where our toggle switch in our power line is pushed down, so we have 12 volts being fed to the circuit. Our button has been released, or it is no longer pressed. It is popped up, so it is open. That means there is no continuity between this 12 volts and the rest of the circuit. And what's happening with that PNP? Well, the base of the PNP is connected through a 1K, 10K to ground, effectively pulling the base of the PNP low. And as long as the base of that PNP is 0.6, 0.7 volts lower than whatever voltage is at its emitter, the PNP will conduct from its emitter to collector. Well, through that 1K to a 10K will definitely pull it lower than 0.6 to 0.7 volts. At this point, what's happening as far as conventional current goes is current's flowing from the 12 volts through the PNP across its emitter and collector, through the diode. We're losing 0.3 volts at the diode. There's a drop due to just what it takes to turn on the diode. If you use a non-Schottky style diode, that drop will be 0.6, 0.7 volts. At this point, well, the current can't go here because of the diode is reverse bias. So it only can turn the corner and go across the coil, activating the coil onto ground. But the circuit doesn't stop there. Once this coil is activated, the flippers that would normally be up here in the normally closed position have been flipped down to the normally open poles, in turn allowing the 12 volts to flow through the piezo, across the contacts to ground, turning on the piezo, and most importantly, also this contact has been flipped, which allows 12 volts to flow from here through the contact back up through the circuit, and it can't go anywhere because of this diode, the bias of the diode. So all it can do is be funneled through the coil as well, keeping the coil onto ground. And now what happens when we press this button again? Well, it'll raise the base of the PNP high, effectively cutting off the PNP. It'll stop conducting, so current won't be flowing this way anymore. But given the way the wiring has been arranged down here, the relay is latched on and current's still flowing through the coil, still keeping the circuit active even though that momentary button has been released or is repressed again. That's the quick version of how the circuit works. If you're still a little confused about that, just check out my video on how to build a latching relay circuit, and in that one I go through in a lot greater detail the notions of these normally open, normally closed contacts, and the way that, and the common contact where the flipper is in relation to where the flipper is when the coil's in an active or an inactive state. But the quick and dirty version is the switch is pressed down on our power supply, the momentary button has been released, in turn pulling the base of the PNP low, which enables it to conduct. So we have 12 volts, crosses the diode. It can't go down to this diode because of the bias of the diode, so it has to go through the coil, activating the coil onto ground. And as soon as that coil is activated, the contacts that would have normally been in the upward position, the normally closed position, have been flipped down to the normally open position, in turn allowing 12 volts to flow through the piezo, cross the contacts to ground, turning on the piezo. It's alerting. While at the same time this contact has been flipped down to the normally open position, which we'll have connected to 12 volts, so current can flow through this contact, back up, cross this diode. It can't go past this diode, so it's funneled through the coil onto ground. In turn, keeping the coil active even if this button is pressed again. So your intruder can press this button all they want, but the circuit stays latched on because of the current that's flowing through this contact through the coil. The coil will be energized whichever way the current comes through, and that button can be pressed, released all day long. And as long as power is still being fed to the circuit, that piezo will be alerting. The only way to deactivate the circuit is to flip or break the connection from the power line. Let's look at the breadboard and build the circuit. At this point, all I've done is connected the left and right rails of the breadboard through these pieces of wire, as well as the upper and lower halves of the breadboard through these pieces of wire. I've put the normally open momentary button in the board, a PNP transistor, as well as our 12 volt double pole double throw relay. Looking at our schematic, the first thing we need is 12 volts through a wire to the upper right hand corner of our momentary button. We have the upper right hand corner of our momentary button, our 12 volt rail. Just need a piece of wire between the two. We have our 12 volt power supply connected through a piece of wire to the upper right hand corner of our momentary button. Now we need, on the lower left hand corner of our momentary button, we need a 10K resistor to ground, and right ahead of that 10K we need a 1K down toward the PNP transistor. We have our 10K to the lower left hand corner of our momentary button right there. We need the 10K in this row to ground, like that. Next, we need our 1K resistor in the same rail as the 10K, pointed down the breadboard toward the PNP, like that. So there's our 1K and our 10K. That's the orientation in the board. Going back to our schematic, we have taken care of this part of the circuit. Now we need a piece of wire from the lower leg of that 1K to the base of our PNP, and we need to connect the emitter of that PNP to the power rail, the 12 volt rail, like that. From the lower leg of the resistor to the middle leg of our PNP. Given the PNP I'm using, you'll need to check the pinouts of whichever PNP you use. Normally with this TO92 package, all you have to do is put the black leg of your meter to the center leg, touch your red lead to this leg, write the reading down, touch your red lead to this leg, write the reading down. Whichever of the two has the higher reading will be the emitter of the PNP, and you'll want to put the emitter toward the top, toward the momentary button part of the circuit, and you want your collector toward the relay side of the circuit. Now we need a wire from the emitter of the PNP from in this row all the way to the 12 volt power supply. And that's how it looks, with this wire from the 12 volt rail over to the emitter of our PNP in the same row of the breadboard as the emitter leg of the PNP. Next, we need a piece of wire from the collector of our PNP transistor through a diode to the row that this coil pin of the relay is located in. We'll also need a diode in reverse bias around the coil, those two coil pins, to catch any back EMF when this coil is energized or de-energized. This just protects the transistor from a tremendous voltage increase and current increase when the magnetic field that's generated from this coil activating collapses. That's all that diode's doing, is it's protecting the transistor. Whereas this diode is protecting the transistor when what current flows up through the rest of the circuit. But we need a piece of wire from the collector through a diode to the row in the breadboard that our coil pins are located on our relay, as well as just a protection diode around the coil. I've added this little schematic on top of our double pole double throw relay just to keep ourselves straight while we're adding in the circuitry. The way it lines up with a regular double pole double throw relay is you have your 6 pins up top and you have your 2 coil pins down below. This is a pretty standard pin out for double pole double throw relays, and all that I have done is rotated that relay and stuck it in the breadboard like that. With the double pole double throw, it's pretty easy, and it's always worth checking the data sheet and making sure that your pin out matches this kind of pin out. If it doesn't, you'll have to redraw the schematic so that it matches. The first thing we need is a piece of wire from the collector of our PNP, the lower leg, to this row in the breadboard, the row that the coil of our relay is located in. Have our wire on the collector of the PNP. Now we need a diode with the cathode pointing down from this row to the row that our coil of our relay is located in. Like that. We have one leg of our diode. The anode of our diode is connected to that wire coming from the collector of our PNP. The cathode, noted by this gray band, the leg attached to the cathode of the diode is in the rail of the breadboard that our coil of our relay is in. Next, we need a diode to protect our transistor from any back EMF generated by the coil. We will locate one leg of this diode. The cathode leg will be in this hole, and then the other one will be over here in that configuration. The cathode of the diode is on the right hand, pointed toward the right hand side. The anode is connected in the rail to the left hand side of the coil. To finish out the circuitry around the coil, we'll need to add a wire from this left hand side to ground, like that. We just added this piece of wire from the rail that this left hand pin of our coil is located in. We have our diode in the same rail, and we have a piece of wire to ground. Moving right along, we'll need another diode from the middle common pin on the right hand side. It'll be the center of those 3 pins. That's your common, where one of your flippers is located. You'll need the anode of that diode toward the common pin and the rail it's located in the breadboard, and the cathode of that diode will be pointed back up the breadboard toward the PNP transistor. We have our diode with our cathode, noted by that gray band, pointed back up toward the PNP transistor. One leg of the diode will go in the same rail that these other diodes are connected in, toward this pin with this flipper attached to it on the like that. Have the anode of that diode in the same row as that center common pin. The cathode of the diode is in the same row as the rest of these diodes connected to this coil pin. We just took care of this part of the circuit, the diode. Now we go to this side of it, and we need a wire from this other common pin to ground. There's the other common pin. It's in this row of the breadboard. We need a wire from this row to ground. The wire to the ground rail. To finish out the circuit, on this last pin of our relay, the normally open pin, we need a wire from it to the 12-volt rail, as well as we need the black lead of our piezo. It would work pretty much in either orientation, but given that it has a red and a black lead, we'll orient it based on those. Then we'll need the black lead of our piezo buzzer to this other normally open pin, and then the red lead of that piezo to the 12-volt power rail. There's the right hand side normally open pin. We need a piece of wire in this row of the breadboard to the 12-volt rail, like that. And then we need to add in our wires from our piezo. The black lead of our piezo will go in the row with this other normally open pin on the relay, like that. And then the red lead of our piezo will go into the power rail. Let's zoom out. we've done everything correctly, we should just be able to hook up our 12-volt supply to the circuit and press our button so it's not immediately alerting. And then when we release it, the piezo should continue to alert even if we push the momentary button, and it won't stop alerting until we disconnect the power from the circuit. I've added one wire, the ground lead from the 12-volt battery pack, to the ground rail of our breadboard. We will push our normally open momentary button down and then connect our power lead to the power rail of the breadboard. What should happen is when the momentary button is released, the piezo should start alerting, and it should not stop even if I press this button again. Let's see if that works. And that's exactly what the circuit did. And the only way I was able to stop the alerting is to remove the power. Remember, you'll just need to put some sort of switch in series with this wire. Just add it in. Cut the wire, put a switch in, and that'll give you the ability to deactivate the circuit once it's in an alerting state. Let's look at this mounted to my door in a crude manner once again, just to see the full effect. I've crudely attached the circuit we just built to my door. The ruler is pressing down on the momentary button, and notice that the power wire is currently not connected to the breadboard. This circuit is not armed until power is added to the circuit. This is where you would need your toggle switch. Let's add power. And let's see what happens when the door is opened. For a quick run through of what just happened is, as soon as I opened the door, the alarm was activated, and then when I closed the door, it remained activated. At that point, the relay had been latched on, keeping the piezo energized even though the door was closed, and the circuit was not deactivated until I pulled the red power wire out of the breadboard. That's just a demonstration of how a latching intruder alarm circuit functions. I hope this video has been helpful. If so, please consider clicking like, as well as consider subscribing to my channel. Thank you.